All right, now that we're recording, again, I'd like to officially welcome you to our presentation on understanding climate change. Dr. Shadbolt was kind enough to do this for us on Zoom. He was actually scheduled to do this live earlier in 2020, but given the state of the world, that didn't quite work out, so we were able to reschedule in this format, and we appreciate his time in doing this and all of you for being here. One last thing that I wanted to say before I introduce him and quit talking to you, and that is, if you're able, stick around for a couple minutes at the end of the presentation. We have just a couple of sort of local connections to this climate change discussion that I'd like to share with you if you want to continue the conversation or be involved in what we're going to hear about today. There are some local things happening that I just want to give you access to and let you know that those are there. All right, so with that, you are not here to hear me talk, so I'm going to quit and turn the floor over to our speaker. Dr. Ryan Shadbolt is from Michigan State University's Department of Geography, Environment, and Spatial Sciences, and he's going to give us kind of a primer, if you will, on understanding climate change. Dr. Shadbolt, it's all yours.
All right, greetings and welcome. I'm a lifelong Michigander myself, grew up in the southern part of the state, and my career thus far has been focused primarily on weather and climate. My graduate degrees say that they were in geography, but I studied climate change and variability for my master's thesis and doctoral dissertation. Since wrapping up my PhD in 2009, I've held a variety of research positions, teaching positions. I was an assistant professor at Northland College in northern Wisconsin for a couple of years before being called back to return to Michigan again back in fall of 2019. My title now is specifically academic specialist, but informally I am the undergraduate advisor and instructor for the Department of Geography, Environment, and Spatial Sciences here at Michigan State. The source of information that I'm going to rely on primarily for today's lecture is this textbook titled Intro to Modern Climate Change by Andrew Dessler. This is the textbook that I'm using this current semester. I'm teaching a large course titled People and Environment, but it's focused on Earth and its modern climate change. I'm going to be splitting today's discussion into roughly 3 equal parts. We're going to be looking at climate change symptoms first, and then we'll talk about the science in the second portion, and then the solutions in our final portion today. In total, this lecture is usually run 50 to 60 minutes, depending on how many questions we encounter along the way. I'm going to start us out looking at Earth's instrumentation record for Earth's global average surface temperature. Certainly we had thermometers predating 1880, but this is showing us Earth's average temperature. So this was really around the time when we had a large network of thermometers on a global scale that we could adequately describe Earth's average temperature. So we're looking at the top part of this figure first. We've removed the seasonal cycle to take out a lot of the noisiness. And so the annual average is the thin gray line. You can see the variability from year to year and between decades. We've also placed the thick black line there to show you a 5-year running mean, which kind of pinpoints or highlights the long-term trends a little bit better. And we can see that the overall trend over that 100 or so years was certainly upwards. These are based on temperature anomalies relative to a baseline of 1951 to 1980, so in the mid to later half of the 20th century. But the important thing is to look at how global temperature changed throughout the entire period. It changed by about 0.85 degrees Celsius throughout that about 140 years illustrated on this figure. Overall trend upwards, but you can see that there are some periods like from 1880 to 1910 was generally cooling, and we had a stagnant period in the middle part of the 20th century from about 1940 to the mid 70s, but the trend has been upward since that time. If we look at it more on a regional perspective, which is what we see in the bottom half of this figure, this is showing us by latitude range. The thin black line is 24 to 90 degrees north, so that's our mid to high latitudes in our hemisphere. The bold dash line is 24 to 90 degrees south latitude in the southern hemisphere, and then the dotted line is showing us between 24 north and south, so that's a tropical depiction. And really what's going on here, why we see these regional differences, is that the northern hemisphere is mostly at the North Pole. It's an Arctic Ocean surrounded by land. And in contrast, in the southern hemisphere, it's Antarctica surrounded mostly by ocean. There's a lot more water present in the southern hemisphere compared to the north. Land and water heats and cools at different rates. Land tends to heat and warm, or heat and cool more rapidly, and we see that definitely illustrated here in the last 20 or 30 years, with the high latitudes of the northern hemisphere warming the most. If we have time, we can talk a bit more later about the specifics of why that might be happening. So, maybe you have doubts about what the thermometer record shows that I just shared with you on the last slide. There are a number of other tools that we can use to confirm that evidence. This figure is showing us the temperature record by thermometer, again, as the thin gray line, but now as the black line, we have our satellite record. Unfortunately, satellites don't take us as far back in time. Our network of satellites really goes from the 1970s through the present, but it shows the same general trend, with mostly increasing temperatures since the mid-1970s. I tend to focus on the longer range. Climate scientists like myself, we usually want to refer to a baseline of at minimum 30 years. And the reason for that is that it helps to remove the year-to-year noisiness and the shorter trends that can be embedded within long-term trends. This shows you an example of, again, the surface thermometer record since the 1970s approaching the present. You can see the overall trend is clearly increasing, though there's variability between years. And you can see we've taken a handful of specific examples where we fit a trend line to smaller portions of this data in order to highlight cooling trends that were embedded within the long-term long-term warming trend. This is a common tactic used by those who are on the skeptic side of climate change. We call this cherry picking, where you literally, strategically choose a starting and ending year so that you can highlight a cooling trend. Climate scientists prefer to stick to the long-term trends because climate, after all, is long-term conditions for a specific region. We can look beyond the instruments themselves and just take a look at what nature is telling us about Earth's temperature. And I think the best tool that we have is ice coverage on Earth. Certainly when Earth is cool, we tend to have more ice. When Earth is warm, we have less ice. Looking at where that freeze-thaw line is, that temperature of 0 degrees Celsius or 32 Fahrenheit is very important, since that's our freeze-thaw, temperature on that scale. This is showing us mean glacier length. So we are monitoring glaciers over time. This is over the last 300 years, dating back to 1700. And we've categorized Earth's glaciers into 5 different latitude regions, spanning both northern and southern hemisphere. You can see that for a number of decades, from 1700 into the mid-1800s, that glaciers were relatively stable. They weren't really growing or shrinking, indicates to us that temperatures were probably stable around that time. We can see that there was a clear turning point here around the year about 1850, and all of these regions, all 5 of them, went on a similar downward trend approaching the present. So it's showing that there is a loss of ice measured by their length. We can also look at ice based on its 2-dimensional surface area. This is going to be collected primarily from satellite information as we're viewing it from above. So we're looking at just the flat 2 dimensions of that ice. This is specifically looking at the Arctic Circle, at sea ice. in the month of September. We use that month because it's at the end of the summer season where we've had maximum melt. So you're able to see the absolute minimum ice coverage captured in this data. The sea ice on the vertical axis here is in millions of square kilometers, so it is using metric units here. And do note that the vertical axis doesn't go all the way down to 0. If you want to do that, you'd have to extrapolate beyond the length of the graph. But we can see clearly that the ice area was decreasing over this period from the 70s toward the present. You can see that there is variability. There was a big news article just a week or so ago talking about the increasing rate of ice loss, and it was really focused on what was occurring here in these later years of this figure that you see here. What's not captured here is the full 3 dimensions of the ice. In that case, we would have to look at the volume to look at the thickness, not just the 2-dimensional surface of the ice. I'm not showing you volume data here today, but it gives a very similar story with a downward trend that's becoming increasingly more steep here in recent years. Next, we can look at ice loss in terms of its mass. So this is in billions of tons of ice lost, and we're showing this as it's accumulating over time. This is starting in the early 1990s, taking us to a date approaching the present, and we're seeing that mass, it's loss here, so that's why you see the value increasing. We have an increase of loss over time. Again, you see that rate kind of going in an exponential rate where it's becoming more steep toward the later years. So a variety of different ways to show roughly the same thing, that ice loss is occurring on Earth. We've expressed that by the glacier length, the glacier area, and the ice mass lost. As we're losing ice that started out on land, primarily over Greenland or over the Antarctic ice sheet, as that ice either falls off of the land into the ocean or melts and then runs off into the ocean, we are literally adding more volume of water to the oceans. In addition, as the planet is warming, land warms rapidly, as we said, but the water is also going to warm. Water does have a higher heat capacity, so it takes a longer time, and that's why you see the magnitude of the temperature change here is very small. What is important about this figure is that it's looking at temperature change not just over the ocean surface. That's what we typically measure. We're usually talking about sea surface temperature, but this is actually looking at data that's collected throughout the depth of the ocean. So it's looking at temperature throughout the entire ocean volume. And so these temperatures should be, the temperature changes here should be very small, but what's critically important is because the Earth contains such an enormous volume of water that even a small change in ocean temperature is going to have large impacts for the Earth atmosphere system in general. And you can see the trends here since about 1960. Here was that stagnant period in the mid-20th century, and from the mid-70s on where we see the increasing temperatures. And you see that's been fairly steep here since about the year 2000. So Earth's water is warming. That just the warming alone causes thermal expansion. So that's going to make the overall ocean volume increase, which is going to result in some amount of sea level rise. The loss of ice over the continental ice sheets that I was talking about a moment ago, as we add that new volume to the ocean, that also increases sea level rise. And that's what's illustrated in this figure from the 1990s approaching the present. This is in millimeters per year. Millimeters are a metric unit. They look small, but just know that there is a lot of regional difference. Some areas experience a lot of sea level rise, other areas not so much. But again, another thing to note here is that that rate has increased to something more like 5.5 millimeters per year here in the last, well, this was from about 2010 to 2015 and the later years of that figure. So this is looking at instrumentation and observations to help us understand some of the symptoms of Earth's warming climate. Now, to put this in a greater context of Earth's history, we're now going to jump back in time prior to our period of instrumentation. This is certainly not all of Earth's history, but we're looking at, in this figure, the last 70 million years. If we start on the left-hand side, at this point, dinosaurs were still roaming the Earth as the primary organisms at that time. Evidence suggests to us that their extinction was probably brought upon by some large impact with Earth that occurred about 65 million years ago. That likely resulted in changes of volcanic activity, wildfire on Earth. There would have been a lot of carbon dioxide emitted into the atmosphere over that period of time, and that brought on this rapid rise in temperature here, known as the Paleocene-Eocene thermal maximum. You see this occurred around 55 million years ago. And then since that time, temperatures have generally been on the decline. Present day is down here. So if anything, this shows us that Earth's temperature throughout much of its history, at least over the last 70 million years, was generally warmer than it is today. Greenhouse gas concentration in the atmosphere was actually often higher than it is today. We're going to take a closer look at what's happening down here in just a minute. But I just wanted to give you the context that Earth historically has often been warmer. And depending on how you define it, as we look at this cooling trend, we could refer to this entire period here as a Cenozoic era ice age, and we are still technically in the depths of that. The gray bar on the right-hand side is going to take us to the last just 4 million years, which is a blink of an eye on a geologic time scale. And so we can take a closer look at what's happened more recently. You can see that there was a lot of variability over time, and you can also see that that variability appears to be increasing as we get closer to the present day, which is now here on the far right-hand side again. Both the last figure and this figure, these predate thermometer records, so we don't have actual temperature values here to create these scales of temperature on the left-hand side. We are relying on what we've referred to as paleo proxies, which is lines of evidence available here on Earth which are analogous to the temperature at the time. Specifically on the right-hand side of this figure, you'll see that shows that it's the change of oxygen 18 in parts per million. What we're using here are oxygen isotopes. Most oxygen on Earth is O16, but there is a presence of O18, and O18 tends to have a higher measured value in the environment when Earth is warmer, because as we warm, we're able to evaporate oxygen, which has a slightly larger mass. That's where the 18 comes in versus the 16. It's in regards to the mass of that atom. And so we're looking at that ratio between O16 and O18 to derive a range of temperature. We're collecting this information from ocean sediment cores. You can see the variability. You can see that here in more recent years, over the last several 100,000 years. Let's take a closer look at that on the next figure here. So this is the last just 400,000 years. Present day is on the right-hand side again. And temperature is going to be the solid line. And you can see that we had this reoccurring cycle of cooling temperature, then it warmed rapidly, cooled, warmed rapidly, cooled, warmed rapidly, cooled, and warmed rapidly. These cycles can be largely explained by relationships between the sun and the earth, things like the tilt of Earth's axis, our distance from the sun. We have also provided on this figure carbon dioxide concentration as collected from ice core analysis. So this is another type of proxy record. Ice cores can tell us information about temperature via those oxygen isotopes. We can also determine concentration of various gases in the atmosphere by literally measuring the air bubbles trapped inside the ice. We can determine the age of that ice because there is a freeze-thaw line that's created with each seasonal cycle over that ice sheet where that ice core is collected. So we're able to create figures like this, and you can see that greenhouse gas concentration illustrated by carbon dioxide is very closely related to the temperature on Earth at the time. And you can see that we reside on one of these current warm peaks. And if the last 400,000 years tells us anything, that if nature continues to repeat itself, we should actually be anticipating another cooling trend. And it just simply hasn't happened, at least not yet, as illustrated by the data. We're going to take a look at this most recent spike. This is what's known as the Holocene epoch. This plateau of warm temperatures over the last approximately 10,000 years. And you can see that from about 10,000 years to about 5,000 years ago, we resided on this nice plateau of warmth. And then we had cooling temperatures that occurred for a couple thousand years or so, depending on how we define the start and end. This is sometimes referred to as the Little Ice Age. And then coinciding with our Industrial Revolution over the last couple hundred years, we've seen this rapid spike in temperature, which is what's illustrated here. We can see that same spike in greenhouse gas concentration in the atmosphere, looking at carbon dioxide or other greenhouse gases. All right, so that paints the big picture of how temperature has changed over Earth's history from 70 million years ago through the present. I don't see any questions in the chat box yet, but feel free to type those in if you have anything related to what we just discussed. Any questions from the audience? All right, well, I'm going to move ahead then. We're going to jump into some basic science and physics of climate change. Looking at energy first, just know that every single object that surrounds you right now, including your own self, every single object is emitting energy over a range of wavelengths. This is what's known as the electromagnetic spectrum. Like I said, all objects are emitting energy. The sun in particular is emitting energy within the range of visible light. And you can see that represented there in wavelengths. It's a length unit of microns or micrometers. And we can actually see the wavelengths that as they relate to the various colors of the rainbow. The basic thing to take away from this is that hotter objects tend to emit energy on the left-hand side of this figure. The sun falls kind of in the middle there in the visible light. So even hotter stars would emit more into the ultraviolet scale. But cooler objects like ourselves and anything at room temperature is going to emit in the longer wavelengths. We emit energy that's within the infrared band, and the same goes for Earth. So if we take a couple illustrations of that, the top figure here shows you the peak wavelength around 10 microns. That's going to fall within the infrared band. This is a good illustration of what's happening on Earth, human body, anything that's close to Earth's temperature. The bottom figure shows us something more resembling the sun, where its peak falls around 0.5, which is close to the middle part of the visible spectrum. What we think of as measuring temperature, and we're doing a lot of that these days as we're screening people's temperature as they enter various buildings, we're actually measuring the power that's emitted by that person. And then there's a mathematical relationship between power emitted and that object's temperature. And so by taking our dog here, what we're actually measuring is the energy emitted, mostly infrared, and we're using a mathematical relationship to calculate the temperature. It's shown here in Celsius. We would convert it to Fahrenheit for most of our daily uses. So based on that general concept, we can estimate not just the temperature of my forehead or my son's forehead when he goes to childcare. We can estimate the temperature of the sun, for example, because we can use instrumentation to observe the amount of solar power that we are receiving, either at Earth's surface or within our atmosphere, and we can mathematically use that to estimate the surface temperature of the sun. We know the approximate distance, around 150 million kilometers. So as that energy, we can estimate that total quantity of solar energy that's coming in. Next question is, what happens to it once it enters the atmosphere? Big portion of it's going to be reflected by clouds, by dust, by gas molecules, by Earth's surface itself. In fact, about 30% on average is simply reflected right back to space. Of the remainder, 70%, about 20% of that is absorbed by the clouds, the gases, and the dust in the atmosphere. And then what's left, 50%, that's what ultimately gets absorbed by the ground. It's absorbed, heats the surface, and then Earth later re-emits that energy back upwards. But because Earth is a much cooler object, it's emitting, instead of visible light, it's emitting mostly infrared light, which is beyond the range that we can visibly see with our own eyes. We can feel the heat, but we can't see it. Now, what's important here is that certain gas molecules in the atmosphere, specifically the ones listed on this slide, water vapor, carbon dioxide, methane, and nitrous oxide, these gas molecules are transparent to the incoming solar light. So they're allowing that solar light to make its way to the surface. Earth's surface then re-emits that energy as infrared energy. But those gas molecules are efficient at absorbing infrared energy. So that energy then becomes trapped in the lower atmosphere as it's held in place from being absorbed by those gas molecules. Those gas molecules will go on to re-emit that energy again, but it'll probably be absorbed by its neighboring molecules, or perhaps absorbed by Earth's surface. And then the process repeats itself multiple times before that energy slowly leaks its way back to space. It's similar to, if it's a cold evening and you're getting in bed and you put an extra blanket on the bed. Those blankets help to keep your body heat close to your body, and that's what warms you. The more blankets you put on, the warmer you will feel. In the similar case here, the more greenhouse gas molecules we add to the atmosphere, it's like adding extra blankets on top of the Earth. Now, water vapor is actually the most plentiful of these, but it tends to be added and removed from the atmosphere pretty quickly through the hydrologic cycle. And also, human activity plays a very little role in the presence of water vapor in the atmosphere. What's important are these other three: carbon dioxide, methane, and nitrous oxide. Human activity plays an important role in all three of them. We see their concentration increasing. Carbon dioxide is emitted. Really all three of these are created by the combustion of fossil fuels, whether it's coal, petroleum, or natural gas. If we take a look at carbon dioxide concentration, we'll take a look at the top portion first. This shows you the last 10,000 years, and we can see that exponential increase here coinciding with the Industrial Revolution. If you zero in specifically on the last 250 years, you can see that again. And if we focus in on our period of record from the 1950s, that shows us two different values on this figure. The gray line shows us the total accumulation of carbon dioxide that's been emitted into the atmosphere in gigatons per year. And then the sawtooth line here in black shows us the actual amount that we observe in the atmosphere. And there's two important things to see from that sawtooth line, because one, it shows us that about half of what was emitted has been taken out of the atmosphere over time. Where's it going? Some of it's going to photosynthesis. Plants absorb carbon dioxide from the air during that process. And a lot of it is also being absorbed by Earth's oceans. So largely this is a good thing because we're able to naturally take out about half of that carbon dioxide from the air. There are consequences of that though, because mixing carbon dioxide with water creates carbonic acid, which means we are acidifying the oceans. When you hear about the bleaching of coral reefs, that is in large part due to ocean acidification. The other part of the sawtooth line is that there's an annual cycle here that's illustrating the cycle of photosynthesis in the northern hemisphere. We have a lot of trees and plants in the northern hemisphere, so it dominates this annual cycle. As plants photosynthesize more during the warm half of the year, it absorbs more carbon dioxide, so that would be the bottom of each of the sawtooth line on here. And then the peak would be during the cold half of the year, which we're in the depths of right now. Similar story for methane over the last 10,000 years, exponential growth coinciding with the Industrial Revolution over the last 250 years. Methane emissions literally coming from the combustion of natural gas, which we're increasingly using, and it's being touted as a clean alternative to coal and other types of energy. A lot of us climate scientists say that we need to move beyond natural gas use as quickly as we can. Next, I want to talk about 5 general forcings of climate change. The first 4 of these are natural. These are what have been in play for most of Earth's history and continue today. Our impact is relatively recent. So the first we can summarize is geologic. This is going to include everything from large impacts with Earth, like the type that led to the extinction of the dinosaurs. Plate tectonics, what was once known as continental drift. The literal moving of land masses across Earth's surface is going to lead to a change in climate. Third would be volcanic activity. Solid material emitted by volcanoes literally blocks incoming sunlight, but the volcanoes also emit carbon dioxide, which can warm the planet over the long term. Second are going to be solar cycles. This is going to include everything from the changes of solar output over the length of the star's lifetime. In fact, over the billions of years, we should expect the output of the sun to increase over time. But we also have smaller 11-year cycles. That's the sunspot cycle. That's we have illustrated here. Excuse me. This figure here only takes us through 2005. But if we extrapolated, if I had more data, we would see that solar output, if anything, tends to suggest cooling temperatures on Earth rather than warming. So we can't conclude that solar output is what's responsible for warming of the last few decades. Earth's orbital and axial cycles. So this has to do with the shape of Earth's orbit on the top and the change in the tilt of the axis, which is what's largely responsible for our seasonality on the bottom. What's important to know about both of these cycles is they are critically important in determining the onset or end of glacial advance and retreat. But both of these cycles take tens of thousands of years to complete. Remember on that one figure we showed, the temperature over hundreds of thousands of years was going through rapid warm and then gradual cool and then rapid warm, and it repeated multiple times. That was largely explained by these 2 cycles in tandem. They cannot be used to describe temperature change within just a few decades like we're experiencing right now. In fact, if anything, as we observe these 2 cycles, they indicate we should be going back into our next onset of glacial advance, and that has not happened. The fourth one is atmospheric and oceanic cycles. Most of these are going to explain basic variability between years, things like El Nino and La Nina. You've all heard of that, which is a change in the surface temperature of the Pacific Ocean. It tends to repeat itself every few years. We are just recently entered a La Nina right now, so that's why we're finally kind of feeling winter time here in the northern parts of North America. But for the most part, the atmosphere and the ocean, they don't tend to be a forcing on a climate change scale. It happens occasionally where we have dramatic changes in atmospheric or oceanic circulation. An example might be like if a massive ice sheet very abruptly fell off into the northern Atlantic. That would greatly disrupt oceanic and atmospheric circulation, probably plunging both the northern half of our continent and the northern half of Eurasia into cooler temperatures. But that happens relatively infrequently. So that brings us to human activity. And, we could be very specific about the ways that we impact climate, but I think we can really summarize it into two broad categories. Certainly, we have the ability to alter Earth's landscape, as we convert forest to agriculture, or we convert agriculture to suburb, or suburb to urban area. All these things change the composition of the surface, which changes the amount of reflection and absorption. So that's going to change the local temperature. Secondly, we alter the climate by contributing gases to the atmosphere, the ones that we just recently described: carbon dioxide, methane, and nitrous oxide in particular, those three. To make things even a little bit more messy beyond just describing these 5 broad categories of climate forcings, us climate scientists also understand that there are feedbacks that are identified in the Earth's atmosphere and ocean system. Here's one example where we start in the top left-hand portion of this figure, and imagine that we initiate a small amount of warming in the high latitudes of the northern hemisphere. Maybe this is initiated by an increase in greenhouse gases in the atmosphere, and we increase the temperature by just a small amount. Earth system is going to respond to this by probably having some amount of ice melting in that area. This is going to change Earth's surface, because as that ice melts, it's going to be uncovering either a darker land surface or a darker water body underneath it, whether we're talking about land or ocean. So the reflectivity is going to be decreased, the absorption is going to go up, which means more energy absorbed, which means more warming, which is then going to accelerate existing ice melt, and you see this becomes a self-perpetuating feedback where we haven't even, as humans, we are no longer adding additional warming. This is adding warming all on its own, naturally at that point. There are multiple examples like this. This is what's known as the ice albedo feedback. Albedo is another word for reflectivity. There are others in regards to clouds, others in regards to greenhouse gases in the atmosphere. Fortunately, there are some feedbacks which offset these runaway warming feedbacks. So that's why we get some amount of balance in the end. But generally, as we observe Earth system right now, most of the feedbacks are pointing toward a warming direction. So in comes general circulation models, or general climate models. With computers, these kind of came along in the mid part of the 20th century. And we'll focus on the top portion of this figure first. Common exercise is that we take the observations as we've measured them by a thermometer. That's what's shown as the gray line. Looks very similar to the trend we looked at before, except it's starting in a different year. Based on everything we understand about natural climate change, the geologic, solar, the orbital, axial, the atmospheric and oceanic cycles, all those things I just briefly described a few slides ago, if we understand all of the physics about those cycles and we're able to represent them as equations depicted by computer code, probably in Fortran originally, we should be able to simulate Earth's climate system, whether we run it forwards or backwards in time. The initial exercise like this is to run it backwards in time. That way we can compare it to the observations we've actually collected. We have the thermometer values throughout the history, so we run the computer models during that period to see how it behaves. The top example is showing us that those computer models running with only the natural forcings, the geologic, the solar, the axial, the orbital, the atmospheric, the oceanic cycles. You can see that it agrees okay in the first half of the 20th century, and there's a clear divergence in the second half. Temperature went up. The model suggested that, if anything, the temperature should have decreased. Based on what we understand now about human activity, how we alter Earth's landscape and the atmosphere, if we include that portion into those calculations, we then get the black line in the bottom portion of this figure. Adding both natural and human forcings together in those calculations, you can see we get a much better fit. It's not perfect. It doesn't have to be. It just has to be good enough that we can understand the trends over the long term. Do the warming trends of the computer simulation mimic the warming trends of the thermometer? And same with cooling trends. You see that does a pretty good job. Gives us confidence that if we then take these same models and run it forward in time, beyond the year 2000 in this case, we run it forward for a few decades, it's likely going to perform in a similar way. This is what really gives us confidence as climate scientists to be able to say that since the mid-1970s, where we saw this divergence here on the top figure, and we get the agreement here in the bottom figure, we can say that since the 1970s, that human activity has been the driving force of this warming trend that we observe here. Okay, so that concludes us with part 2. See a couple of just a couple quick comments, not actual questions there in the chat box. But if you have any questions along the way as we continue here in this final portion, feel free to drop them in that chat. So based on everything we've talked about thus far, I want to conclude this with some recommendations of what we can focus on going forward. And I think this particular figure, although it is a little bit outdated, you see it only takes us through about 2005. It is important in terms of identifying where I think we can focus our not to use a pun here, but where we can focus our energy in the decades to come. This is looking at comparing 4 variables to a baseline of 1970. These 4 variables are used to describe environmental impact as illustrated by carbon dioxide concentration in the atmosphere. We know that carbon dioxide concentration as a greenhouse gas is going to go up as Earth's population goes up. As there's more of us, we're all consuming, so all of us are going to be increasing that impact on the atmosphere to some degree. Population is illustrated by the plus signs. Relative to 1970, you can see it's gone up steadily. The good news is that fertility rates on a global scale are declining. And just to be clear, when I say fertility, I don't necessarily mean like a woman's ability to have a child. Fertility rate, by definition, in this case, is used in terms of the number of children a woman actually has. So it's based on our rate of increase. So that rate of increase is declining, although you can't see it well on this figure. Even in developing nations where families tend to have more children than what we do here in North America, we are seeing rate of increase on the decline, but it is still going to increase. It is a positive value. So there's not much that we can do about that. In order to lift those existing people out of poverty, we need to have income for those people. And we're illustrating that by gross domestic product here. And you can see it is very closely related to population as the black solid line. We're going to likely see that continue to climb as population climbs. So if we want to lessen environmental impact, we need to focus on these other 2 variables where we see they've actually have declined over time. And we're illustrating this. It's really what it's getting at is energy efficiency. And we can describe that based on carbon intensity, which is the dotted line, and its units are carbon dioxide per joule. So it's the amount of carbon dioxide that's emitted for each joule of energy we consume. And then the energy intensity is the dashed line. That is in joules per dollar of GDP. So it's how much energy you get for every dollar you spend. So that's also an efficiency unit in a way. And we can see that both of those decline steadily, and those continue today if we had the data on this figure to show you. And I think that's where, you know, as we transition away from conventional fossil fuels as sources of energy and move more toward alternative and renewable sources, and as we take existing technology, you know, the example of moving away from incandescent light bulbs to compact fluorescence and now to LEDs, that is increasing the efficiency over time. We need to keep moving in those directions. looking at some model data for the 21st century, RCP here stands for Representative Concentration Pathway. The 4 different values represent difference of power added to the atmosphere relative to the pre-industrial revolution. And we use 4 different values here to represent a range of scenarios. Unlike when we modeled past, we knew exactly what the population, the temperature, the atmosphere was like during that period of instrumentation. We don't know what the future is going to be like. We can make some good guesses, but we don't know exactly what the population will be. We don't know exactly what our emissions will be. We don't know exactly what the greenhouse effect impact will be at that time. So that's why we provide a range of scenarios. RCP 2.6 is going to be the more aggressive approach of lower population growth and a more aggressive move toward transition to renewable energy. The black line is, think of that more as the business as usual. If we had remained on the current rates of consumption in the year 2000, if we stayed on that trend, that's where we would be at the end of this century. This is showing carbon dioxide emissions in gigatons per year. Based on one of the figures I showed you earlier, you know that about half of this is removed from the atmosphere from ocean absorption and through photosynthesis. So what actually we measure in terms of concentration is going to be a different value. So we're showing you that here in parts per million. Today we're at about 415 parts per million. So this shows you the range. Ideally, to keep warming at less than 2 degrees Celsius compared to pre-industrial times, we should be trying to aim for that 2.6, which is the most aggressive approach there. I'm not going to get into the mathematics of this today, but our understanding of how carbon dioxide, how it relates to temperature, that brings us to this figure. So this shows us the actual temperature increase connected with each of the scenarios. If we could follow the 2.6 scenario, what this is telling us is that we would see by the end of this century about a 1 degree Celsius increase compared to the end of the 20th century, and then compared to that to pre-industrial time, we had warmed about 1 degree Celsius. So in total, it would be about 2 degrees Celsius warming compared to pre-industrial time. So that's the goal. It's going to require a lot of change on both a global and national, regional, and local scales to get there.
Design and apply solutions.
So there's, in summary, we can conclude, I think, 3 approaches to making this transition. We can take the adaptation approach, which is responding with technology as climate change occurs. Simple example would be allowing sea level rise to happen, but we respond by building taller levees along our coastlines and seawalls, things like that. Mitigation is a little bit more of an aggressive approach where we try to head off the climate change before it happens. So that would mean making the transitions to renewable forms of energy and trying to emit less carbon dioxide in the first place. And then finally, geoengineering. This is the most aggressive approach of all, where we literally try to alter Earth's system in ways to minimize the impacts of climate change. And there's 2 main ways that we can do that. One would be to alter Earth's landscape so that we can increase the overall reflectivity of incoming sunlight. And then the other approach is to try to alter the amount of solar energy that can even make it to Earth's surface. And these would be large undertakings. There's a variety of approaches that are under study. I would argue that probably to be successful, we're going to have to undergo some amount of all of these things: adaptation, mitigation, and geoengineering. Now, one of the things I want to leave you with here today before we conclude is that in the media, we're getting a little bit better at this in journalism, but I think historically in the last few decades, there has generally been this approach of equally cited population. Sorry, I'm having a little bit trouble articulating that, but we usually illustrate arguments in the news as having just two sides that are of equal size, where you have someone arguing pro and someone arguing con. And so it looks like things are equally distributed. But for a number of years, Yale has been undergoing a climate study, and you can take this quiz. The link is provided down here. It's a very short, just 4-question, multiple choice quiz. And based on your responses, they will categorize you in one of what they call the 6 Americas by these 6 categories. And it ranges everything from alarmed about climate change there on the left to dismissive. And this was from one of their more recent samples of over 1,000 US citizens. And you can see that it is not equally distributed. In fact, most of US population considers themselves, well, whether they know it or not, based on the answers they provided, they're either alarmed, concerned, or cautious about climate change. So I think this is good news. It shows that most of us actually are concerned and would probably support legislation or federal tax dollars that would be going toward various efforts to help, either adapt, mitigate, or geoengineer ourselves out of a climate change scenario. Unfortunately, it's those folks, especially in the dismissive category. There's not very many of them, but their voices are often loud, and those voices get a larger proportion of airtime than they probably should have. Finally, what we can do is continue to learn about climate change. And I know I'm speaking to the choir of those of you who are here because you've devoted the last hour to this topic. So you must have some passion about learning about this already, but I want to encourage you to continue to do so. Make sure that you talk about these subjects with your friends and family, and make sure you visit the ballot box and vote with climate change in mind, not just on the federal level, not just on years when we're voting a presidential ticket, but all of the regional and local elections as well. And in many ways, those decisions are even more important and more fast moving than what occurs at the federal level. With that concludes our talk today. I am happy to answer any questions you have. I'm going to take a look at the chat box.
Ryan?
Yes.
This is Keith Shusson. I wanted to say, yeah, much of what you say is obvious, probably to this group here, but I think you did a very good debunking of very common myths. You have a very good progression of your data presentation. It's very basic, and I think you could reach a big audience with it. It would have to be brightened up with some pictures, I think. Yeah, I can see how you really try to, soften the blow, as it were. I'm really, really interested in solutions. I've been learning about it for about 45 years. If you want to take a picture of it, I would love to talk to you more about it afterwards too. I got great examples of people doing miracles in landscapes, and they're my models for my own design work as well. So yeah, it's all about managing carbon and water and everything else that flows across the land. And that's subject to good design, I'm happy to report.
Thank you.
Thanks. I wanted to say thanks. Yeah.
You're welcome.
Yeah, by the way, I got great pictures, images, and sources for you if you really want to dive even deeper.
So let's take a look at the chat box here. It says, do you think the information you are providing here should be part of high school curriculum? Are you aware to what degree this is happening? Oh, I could give a whole lecture on that. It all depends on the teacher. It all depends on the course. Some schools include earth science curriculum, and this could easily be included there. Some schools have environmental curriculum. Unfortunately, there are not very many districts which specifically have classes in either meteorology or climate change. part of why I like to do these lectures is to try to include secondary schools, K through 12. Hopefully once we're able to do things in person, I can start to do more outreach events with local school districts. But what I can say from my experience in teaching over the last decade or so is that some education programs do include, they don't necessarily require, but some do include a basic course on weather and climate or earth science. And so for those teachers in particular who have had some exposure to these topics, they would have the expertise to be able to work it into their curriculum. And certainly some are going to do that more than others. But I personally would like to see more climate change curriculum in secondary education.
Do you know if the core curriculum in Michigan says anything about climate change?
The core secondary education curriculum?
Yeah. Just not sure.
I am not positive about that. I'm more familiar at MSU. I'm more familiar with the College of Social Science because that's where my department is. So, you know, social science students are going to be taking a lot of courses in disciplines like history and economics and political science. Some of our geography courses are in their curriculum. Probably the students who are more likely to get exposure would be those in the College of Natural Science here at MSU. And that's going to vary depending on what institution.
But it seems like we need some kind of overall directive to the education system that this is a topic we cannot be missing. This is too important. You know, if we're worried about the alphabet, we should be worried about this. Kinda.
Yeah.
If I may briefly, I just want to put in a plug for the Upper Peninsula's University in Marquette and a very, very, very strong representation for sources for all this kind of data. I'm happy to see it taken hold there, as it were. People taking on real practical solutions with things like permaculture, managing animals completely different on landscape, managing trees completely differently, putting wetlands back into the landscape, and so on and so on. MSU's got some great stuff going on too, also in the UP, coincidentally, at their farmer training center up there, and they're teaching organic farming and polyculture farming, and it's really quite wonderful. And host an annual convention, so it's pretty awesome. MSU has great roots. Liberty Hyde Bailey and so on and so on. Anyway, I'm just saying, just a plug. I could shut up now.
Thank you. I want to take a look at a question that was asked by Bruce. He says, if we become carbon neutral by the year 2050, how much longer would greenhouse effect continue to drive warming due to existing level of atmospheric loading? What I would like to say about that is if we look at Earth's relatively recent history, carbon dioxide concentration in the atmosphere naturally was in the range between 180 and 280 parts per million. And as I mentioned today, we are currently around 415 parts per million. So we're well beyond what has been naturally expected throughout Earth's recent history. I cannot say for sure, you know, will we be carbon neutral by a specific date? I mean, certainly, you know, various people are coming up with targets. But what is important to note is that the greenhouse effect is critically important for our survival. In fact, the natural greenhouse effect existed long before our existence, and it is what allows Earth to be at a comfortable temperature for us. In fact, we estimate that Earth would be about 33 degrees Celsius on average cooler than it is today if we were to remove greenhouse effect. Currently, Earth's average surface temperature is around 15 Celsius, and so 33 degrees cooler would be minus 18 Celsius. So the life here would be very, very different without the existence of a greenhouse effect.
What I'm really trying to ask you, Ryan, is won't the warming from human activity continue for several more decades, even if we became carbon neutral at an optimistic 2050? That is optimistic, number one. As you say, who knows when exactly that might occur. But even if we get there, won't we continue to warm because of the residue of previous decades of human activity driving temperatures higher than the natural greenhouse effect?
Right. You're exactly right there. That what I did not talk about explicitly today is that I did mention that greenhouse gases like water vapor remain in the atmosphere for a very short time. But greenhouse gases like carbon dioxide, that's a very different story. They have a much longer lifetime in the atmosphere. So the carbon dioxide that we are emitting today, much of it is going to be in the atmosphere after we're long gone. Some of it will be there for just years, some of it will be there on the order of decades, some of it will still be there even centuries from now. So yes, the energy that we consume today has a legacy that long outlasts us. And so even if we are carbon neutral by 2050, there will still be a legacy of human created climate change beyond that time.
Yep.
Thank you.
Ryan,
Let's take a look at, yes.
I'd like to know if you are aware of any grant sources or either in community groups or for municipalities for implementing any actions to reverse or mitigate the climate crisis.
I'm not aware of any like specific grants offhand. But in terms of agencies, you might want to look at the federal level agencies like the Environmental Protection Agency, EPA, the U.S. Geological Survey, which is USGS, National Oceanic and Atmospheric Association, that's NOAA. Those are some of the agencies which have the, and NASA too. Those are some of the federal agencies that have the greatest stakes in these questions and trying to find solutions.
If I may, I'll mention, because I'm a member of the city council here in Montague, and we adopted a climate emergency resolution roughly a month ago. We're going to have an update. The resolution mandates that this year and again annually over the next many years, we target reducing activities by the city government to carbon zero by 2040. And so the first take on that will be presented this coming week, February 10 at 6 p.m. on a Zoom format by our city manager, Jeff Out, and the Climate Action Council. If folks here on this Zoom today are already on the mailing list, email list for notification from the White Lake Area Climate Action Council, you don't need to do anything more. You will receive a notification, but please spread the word. among friends and neighbors, because that'll be a chance to look at not just what will city government do in their purchasing and their activities, but also what role will city government play in educating the public. And similar cities, small and large, notably Houston, Texas, which is not a liberal hotbed, it's a rather conservative gas and oil dependent economy in Houston, has targeted 2040 for carbon neutral status of the city government. So there's many other localities, as Ryan referred in earlier in his lecture. It's down at the local level where specific actions, purchasing and activity can occur. And an example might be that presently in Montague, we say that if your lawn is over a certain length of height of the grass, the city can give you a ticket or come and mow it for you and charge you money for mowing your lawn to get it back to the prescribed height. But a different approach would be to allow prairie or similar things like Keith Johnson mentioned earlier here today, similar activities in your yard to make it into a better landscaped carbon capturing type of landscape. And if we explicitly allow that in our city ordinances, then one by one, individuals, private individuals, can change their conduct and change the carbon absorption of their little parcels of land here in the city. So we're going to hear an update February 10, 6 p.m. Via Zoom here locally.
Thank you.
And thank you,
Thank
Bruce,
you
for
for the-
mentioning that. I have been putting that information from the White Lake Climate Action Council in the chat. So if anyone wants more information on that or how to reach them, their Facebook contact is there, as well as a petition that they're currently circulating. So you can find out more about all of their work that they've been doing locally as well. So the dates for the Montague Town Hall meeting is there, and all of that information is in the chat, and we'll also include it when we send out the recording for this as well. So if anyone that you know wants to find out about that information later, we'll have that available. Any last questions for Dr. Shadbolt before we let him go escape? Thanks.
There's a lot of them in the chat. Sorry, we probably don't have time to get to all of them, but I did want to mention a couple of you asked about my contact, my email. You should be able to still see it here on the slide. Just my last name at msu.edu. So if you need to reach me at some point after today's discussion, that's where you can find me.
Well, we appreciate all of the information. You've given us lots to think about and digest and hopefully put into action here locally. So thanks. And again, thank you for being with us Zoom style, even in the midst of all of the craziness this year. This is important information we wanted to share. So thank you everyone for being here. And yeah, I will put that information in again in the comments before I close out our session here. All right, I will quit talking and let Dr. Shadbolt go, and take care everyone. Have a good afternoon, and we appreciate you being here.
Thank you.
Thanks, Amy. Thanks, Dr. Shadbolt. Hi, everybody.
All right, if you're waiting for that information again here, give me just a moment.
Great presentation. Thank you.
Thanks for being here. We appreciate it. I'm so glad we got to do that. All right, let's see. There's the Facebook page for the White Lake Area Climate Action Council again, and here's the petition information that's regarding the Whitehall area specifically. And And here's the Montague dates again. And please know that all of that information will be included also. I will send out the recording as soon as it is ready, and we'll include all of that, all of those dates in that recording as well. And with when this recording is posted on our social channels, this information will be there. So if there's anyone that missed it, that you want to see that information, it will be available in every place we can make it so. All right, take care everyone. We have another presentation coming up at the end of the month on, I think it's February 24th. Not related to climate change, but related to our great state of Michigan and some of the unusual things you might find traveling across it. We can't do a lot of traveling in our cars right now, so we're going to do a little virtual traveling with Michigan back roads. So you can find out more about that on the library's website. And that is all we have for you today. So take care, everyone. Have a good afternoon.